Hi everyone, my name is Utkarsh and I'm a postdoc at the University of Wisconsin-Madison. In my talk, I'll be talking about a robust neural network-based method for estimating primordial non-Gaussianity of the local type. The work that I'm going to talk about is done in collaboration with Moritz Mojmeier, who is an assistant professor at UW-Madison, and Kendrick Smith, who is faculty at the Perimeter Institute. Since my talk is going to be about the local type primordial non-Gaussianity, I'll begin by giving a quick intro to primordial non-Gaussianity in general, which I'll just call PNG. And as its name suggests, primordial non-Gaussianity refers to any possible departure from Gaussianity for the fluctuations in the primordial scalar fields. So far, we have not detected this signal, so we do not know whether primordial fields had Gaussian fluctuations or if there was any non-Gaussianity in it. But if we want to detect it, it will be a very powerful probe of the primordial universe, as it can tell us about the field contents of the early universe. In particular, the single field floral model, which is one of the most popular and the simplest models of inflation, predicts a zero or near zero level of primordial non-Gaussianity. So if we want to detect any PNG, it will rule out the single field floral model. And these are some of the reasons why cosmologists are really interested in detecting or constraining this parameter. In order to look for PNG, one can look into cosmological data sets, for example, the CMB map. But in order to analyze those data sets, we need a statistics that is sensitive to this PNG signature. And the lowest order endpoint function that is sensitive is the pi spectrum, which is defined as the ensemble average of the product of waves at three different wave vectors, which sum up to form a closed triangle. And depending on the relative sizes of the wave vectors and their orientation, the pi spectrum can be broadly classified into different shapes, and different models of inflation or primordial physics predict pi spectrum signal to peak in one shape and not in another, or vice versa. For example, the local type primordial non-Gaussianity predicts pi spectrum in the squeeze limit, where two of the modes of the triangle are much larger than the third. So the local PNG, which is the topic of my work, can be written down in this phenomenological model, where you write down the primordial non-Gaussian field in terms of a Gaussian field with a quadratic but local correction added to it. And this leads to non-Gaussianity, and the level of non-Gaussianity is modulated by this parameter FNL that we want to detect or constrain. And as I said, this local PNG sources pi spectrum in the squeeze limit, where its magnitude can be expressed in terms of the product of the power spectra. And people have looked for this pi spectrum signature in the CMB maps. And the current best constraint comes from the Planck collaboration, which has found that FNL is consistent with 0, but their measurement has an uncertainty of 5, which means that we cannot really conclude whether FNL is exactly 0 or if it has an order 1 non-zero value. So in order to prove smaller values of FNL, we need to reach much higher sensitivity. And a highly motivated target is reaching uncertainty levels of order 1. But unfortunately, you cannot reach this level just by analyzing CMB maps, because we have already nearly hit the information limit on FNL that CMB maps have. And because of this, the focus has now shifted to the other cosmological field that we have access to, which is the large scale structure. And the prospects of detecting FNL from LSS is very promising as well as very challenging. It's promising because a lot of 3D large scale structure data is going to become available to us in the very near future. But it's challenging because the primordial non-Gaussianity signal in LSS is not as pristine as it is in CMB maps. And that has to do with the fact that evolution of structure from an early time to late time today is a very non-linear process which introduces non-Gaussianity of its own. And so the primordial signal gets swamped by your secondary non-Gaussianity. Nevertheless, people have proposed several approaches, including the squeezed pi spectrum analysis, where people often restrict themselves to only large scale modes, which are still very linear and easier to model. People have also looked at cluster abundances, which are sensitive to the skewness of pyramidal one-point function, and thus to the FNL parameter. But the most promising and the cleanest signature of primordial non-Gaussianity comes in the form of a PNG-induced scale-dependent bias in the tracers of large-scale structures like the halos. So in a universe with the Gaussian initial conditions, the power spectrum of halos on the largest scale will have a constant bias with respect to the matter power spectrum, which can be seen here in this figure. Where on the larger scales, there is a constant offset between this green curve and this blue curve. And this is for a universe where FNL is 0. But in the case where FNL is not 0, the total bias of halos acquires an additional term which has this 1 by k square dependence. And because of this dependence, the power spectrum now acquires characteristic shape dependence. And people have used this shape dependent feature in the halo power spectrum or power spectrum of other tracers to constrain FNL. And over the last 15 years, several groups have done this analysis, and the best result we have so far is an order 10 constraint on FNL that comes from the POS data set. I would also like to mention that this signature is a very robust signature which does not get affected by uncertain baryonic values happening on smaller scales, and is something that cannot be faked by any other astrophysical process. So this is a very clean signal as opposed to any other signal of PNG. And now in this slide, I'm going to talk about the origin of scale-dependent bias. This is probably going to be the most important slide of my presentation because the induction that we built here is going to lead us to the formalism that we put forward in the coming slides. So if we re-express our primordial non-Gaussian field in terms of Gaussian field, where the Gaussian field is decomposed in terms of a long wavelength contribution and a short wavelength contribution, and we plug this in and work things out, we'll find that the presence of a non-zero FNL leads to a coupling between small-scale modes and large-scale modes because of this term. And because of this coupling, the RMS fluctuations, the local RMS fluctuations of the field start getting modulated by the long wavelength mode phi L. And because the late time halo abundance is sensitive to this sigma 8 local quantity, the halo in turn starts getting modulated by phi L. Now, the bias of halos, which is defined as the response of halo abundance, local halo abundance to long wavelength perturbation, is a constant in a universe with Gaussian initial condition. But in a non-Gaussian universe, by which I mean a universe with local non-Gaussianity, non-zero value of FNL, the halo abundance additionally becomes dependent on phi L through its dependence on sigma 8 local. And because this phi L is related to matter perturbations through the boson equation, and we end up acquiring an additional bias term, which has this 1 by k square scaling. So just to reiterate, in a non-Gaussian universe, a universe with the local non-Gaussianity, there's coupling between small-scale primordial modes and large-scale primordial modes. Because of this coupling, our RMS fluctuations, local RMS fluctuations, start getting modulated by phi L. And because the halo abundance responds to this local fluctuations, the late-time halo abundance also starts getting modulated by this phi L. And since this phi L is related to matter perturbations on large scale via the boson equation, which has a 1 by k square dependence, our bias ends up acquiring a 1 by k square dependence term in addition to the constant bias. But there's nothing uniquely special about the halo abundance. Any other statistics, local statistics that responds to local modulations in sigma 8 will also end up acquiring a 1 by k square dependence, just like what halos do. And guided by this simple intuition, we design a neural net with a small receptive field And we feed in matter density fields obtained from running an n-body simulation. And so we feed this matter simulation in. And the goal here is to learn a mapping between the matter distribution and a field phi, which is built out of local estimates of sigma 8. So we are trying to learn a map phi, which at each point estimates local sigma 8 directly. And the way we do it is by minimizing this loss function, which is just trying to minimize the error between the mean phi value outputted by the neural network and the true sigma that was used to run that n-body simulation. And in order to train this network, we use QoT simulations, a subset of QoT simulations, which have fixed cosmology, but have sigma 8 varying between 0.819 and 849. And so we train our network using this data set. And based on the intuition that we have from the behavior of halo over density field on the large scales, we conjecture that the pi field that we end up obtaining would have a similar bias model as that of the halo field. So it will have a constant bias on large scales, and depending on the value of fn, it will also have a 1 by k square dependence. And to validate this bias model, we run a suite of simulations where we set our FNL value to a non-zero value of 250. We run it forward using an embodied code, and we process it to produce the 3D matter field. And then we feed that 3D matter field to our already trained neural network to get an estimate of the phi field. And when we calculate the bias of the phi field, we recover that 1 by k square scaling that we expected based on our intuition. And so this 1 by k square scaling is similar to what we had for the halo density field. And this is the signal that we are now going to use in a very analytical framework to constrain FNL. And I should just mention that in our entire training process, the neural network did not see any simulation which had a non-zero FNL. So we trained our simulation with only Gaussian initial condition based simulations. And even after training on those set of simulations, we are able to recover this 1 by k square scaling when this neural network is applied to a non-Gaussian simulation. And the reason is that the neural network has done pretty well to estimate sigma 8 local. This dependence comes from there. More broadly, unlike other black box approaches or applications of neural networks, our approach has this nice idea that we are only using neural network to produce an intermediate data product, which is our pi field. And that pi field can be subjected to all kinds of diagnosis and validation, and therefore can be thoroughly analyzed. For example, this recovery of 1 by k square scaling is a very strong validation of our neural network approach. We also recover constant noise on large scales, which we had predicted. And we also find 100% correlation between the matter field and the pi field. Moreover, we can do many other cross checks. We can do several field level null tests. We can cross correlate our pi field with noise maps. We can cross correlate with other cosmological fields, and we can do all kinds of checks whatever we want. So once we have done our validation and we have a very fully trained neural network that spits out the pi field, we proceed with a very analytical likelihood analysis, where we analyze 100 simulations run with an FNL of 0. We define a likelihood model that is dependent on 3 parameters: the halo bias, the bias, Gaussian bias, the FNL, and noise. And we feed into it data obtained from the simulation. So we feed into it the matter field as well as the pi field on the very largest scales using a K-max cutoff of 0.014 MPC. And we find in our analysis that by analyzing matter and pi field, we end up constraining FNL to value close to 2. But if we do the same analysis and instead of using pi, use the halo field, we get a bigger error bar, which is close to 7. So just to summarize and rephrase, a halo plus matter based analysis is kind of the cleanest and most state-of-the-art analysis that we have for constraining FNL. And the framework that we are proposing improves upon those error bars by a factor of 3.5, which is quite a significant improvement. And finally, we rerun our analysis pipelines on another suite of 10 simulations, which were run with an FNL of 250. And here again, we end up obtaining an unbiased estimate of true FNL with a similar 3.5 factor improvement in the error bar. This can be seen here. We are working on extending our analysis beyond this. So we are working on extending our approach where instead of feeding in the matter density field, we feed in the galaxy catalog or galaxy density field, which would be a more realistic analysis. We also want to analyze simulations with baryonic feedback to determine the sensitivity of this primordial prefactor that appears before the FNL parameter, which is likely sensitive to the baryonic physics. We also want to explore other neural network architectures, other hyperparameter choices, as well as other transformations. For example, the wavelet scattering transform that has recently captured become really popular. And as we mentioned, any statistics that is sensitive to sigma local is gonna produce this 1 by k square scaling. So our approach, our formalism can equally well be applied to squeeze pi spectrum, tri-spectrum, and other statistics, other local statistics. And we also want to study parameters beyond FNL. For example, we can look for GNL signatures as well using our own formalism. Finally, to summarize, in our work, we have proposed a robust and interpretable CNN-based approach for constraining the local type primordial non-Gaussianity parameter FNL. Our method is robust to small scale baryonic and galaxy formation uncertainty because this 1 by k square scaling appears on the larger scales and remains preserved. And unlike a fully black box CNN approach, our formalism is more interpretable as well as more diagnosable. And we get, based on our simulations, we get a factor of 3.5 improvement on the errors on sigma on errors on FNL in comparison to a traditional hero-based analysis. But note, however, that the CNN gets to see the matter distribution and it learns the matter to pi mapping, where the matter field is unobservable in reality. So we want to learn halo density or galaxy density to pi mapping, which is a work in progress right now. I would like, hopefully, we would have updates on that soon. Thank you for checking out my video, and if you have any questions, you can tag me on Slack or you can come to the live session that is going to happen on 4th of July. Thank you.